This is welcome to the Geology of Jura. This is a follow-up to the talk I did last wee while on Isla. You could see Isla in the background here. This is Isla. These are the paps of Jura. So this is the north end of Jura. And those who know Jura a little bit know that it's made mainly of Jura quartzite. And this, you can see this is quite a nice example of the southeast dipping. This is looking south. This is looking southwest down the strike, and this is the dip of the Jura quartzite. And we've got tons and tons of Jura quartzite on Jura. So let's move on. Where is Jura? Well, this is just a bit of a geography lesson for those who are unfamiliar with Jura. Next to Isla, but more remote than Isla, because you have to get a ferry, the Calmac ferry from Kennercraig or from Oban into Port Ascaig, then the wee ferry, this one, across the Sound onto Jura. If you're not taking a vehicle, you can get the quick rib trip from the Phalanx into Craighouse in the summer. Obviously not at the moment, but when we get back to normal life, if there is ever such a thing, this is how you get to Jura. So there it is, but quite remote because of that. Okay, 196 people live on Jura. It's a lot less than Isla, which is about 3,000. Maximum population was about 1,300 some time ago, and there's a lot more deer than people, about 6,000 deer, and it's sort of 1, 2, 7. I think there's 7 estates own the whole of Jura, 6 of which are absentees. Only Ardlassa, the guy, lives there. There's one road called the Long Road, which goes from the ferry to Isla, loops around the southern end of the island, goes through the small capital, the large settlement of Craighouse, with one pub, one distillery, one school, one primary school, and then it goes up to the end and ends there. The public road ends there, about 4 miles south of Barn Hill, of George Orwell fame, and of another 7, and then up to Corryvreckan. So you've got Barn Hill, Corryvreckan, a place called Inverlussa, which we're going to visit. Tarbert is at the Narrows, and we've got this loch Tarbert that almost cuts Jura in half. And then a little place called Ardfinn. So we're going to go to all of those places in turn, but we're going to start up in the north. When you get off the ferry, you come through Craighouse, just to get on a bit of geography for you. Here's the Jura Hotel in Craighouse. This is one of those typical Victorian paintings with these huge mountains looming over the village, which is, but I think this building is the same building as that, just from the other direction. So not a lot has changed, and they're obviously a big distillery next to the hotel. That's Craighouse. So, a bit of geology. So, as I say, Jura is dominated by the Jura quartzite, which in this map is yellow, which is a sort of meta sandstone. As I say, it dips to the southeast, which is this way. It dips this way. Everything is dipping this way and younging this way. So these grey rocks here down the southern southeast flank of Jura and on the southern half of Isla, which joins up, are slightly younger than the Jura quartzite, which is here. Yeah, and you can see I've got a stratigraphic column here, and the Jura quartzite sits here in the Dalradian, which is it's round about 650 million years old, and the grey stuff here is the slightly younger stuff on top, and that's the main geology of Jura is the Jura quartzite and this slightly younger stuff plastered on the southeast flank of it. But it looks very boring, but it is not boring. Let me tell you, it is not boring. You're going to have an interesting wee time now. So there's a geological column for Isla and Jura sort of combined. We talked last time, if people who were on the last talk, all about the rins and the Collinsy group. And here's the Jura quartzite, and we're going to just be concentrating on this little bit of the stratigraphy here. So the top bit of the Jura quartzite and some formations known as the Jura Slate, the Scala Conglomerate, and the Port Ellen Phyllite. They all occur up here. There's the age. They are around about 650. The Port Ascaig Tillite, slightly older at 700. And the Phalanx volcanics dated at around about 600. So sort of sandwiched between the Phalanx volcanics at 600 and the Port Ascaig Tillite at 700. So we've got this succession of meta sediments, sedimentary rocks that have been slightly metamorphosed but then belong to the Dalradian. Yeah, those of you know that. And here we are, 650 in the top bit of the Precambrian or the Neoproterozoic, well before the Cambrian at 550. We're about 100 million years before the Cambrian explosion of life. Okay, I think most of you probably know all that stuff. So let's take you on a few geological localities. I'm going to quickly run through a few of them. Halfway up the top, near the top end of Isla, near the end of the road, is a place called Ardlussa, where they make the gin at Lussa Gin. And this is where the estate house is at Ardlussa. Just south of that is Lussa Bay, and a place called Inverlussa and Lussa Given. And I've got a little excursion I'm putting in the new book I'm writing, which is going to take you round the coast here. And you can see I've got Jura quartzite marked in yellow, and these things called the Scala Conglomerate and the Jura Slate marked in sort of orange color, and the slate, typically, I'm trying to draw it as a sort of a grey colour, so you can see that, and you can see there's a sort of bay where the slate is. So let's just have a little wee walk around here. I'm not going to stop at every locality. I'm just going to just take you on a whistle-stop tour around Inverlussa, because it does give you a sort of idea of a good idea of the stratigraphy of this succession, and then we can talk about how it evolves. So this is a nice typical remote little Jura settlement, couple of wee houses at Lussa Given, and a little beach down here, very pleasant. And the first rocks you find on the foreshore here are is a bit of Jura quartzite. As you say, there's lots of it in Jura, but it's quite obvious here. You see quite a lot of cross bedding. You can see this sort of bed here is thinning out this way. It's sort of maybe there's sort of a ripple, a big cross bed going this way, and you could argue there's some possibly going the other way over here, and that's quite a feature of Jura quartzite, is that you get these cross-bedded sets going different directions, and this has led to the belief that a lot of this is tidal, that tides, a very strong tidal influence in the deposition of these shallow marine sands, and sort of climbing ripples and mega ripples and dunes prograding in different directions at different times depending on what the tide was that deposited that particular bed. What's astonishing about the Jura quartzite is that there's over 5 kilometers of it now, and that's post compaction. So God knows what it was like when it was soft and squishy. Probably more like 6.5 kilometers of it, which is a lot of sediment, and it's all pretty much the same. So it's a very unusual deposit. As you walk around the coast, you sort of scramble over seaweedy bits and around here, and this is at the top of it. It gets quite sort of bedded, top of the Jura quartzite. What some in the old days you'd call these flags. They were probably used for sort of built walls and building walls and stuff like that. Less of the cross-bedded stuff. This is the flaggy stuff, and then this low bit here is the first sign of the slate, or the meta mudstone, as we should call it, that lies above the Jura quartzite. And then in the cliff, you find there's a quarry in the slate, as there often is on Jura. Here's some sort of cleave meta mudstones, and you see there's a bit of deformation going on in here. You've got sort of bedding coming through here, and then some sort of vertical. There's a sort of this looks like it's been pushed up vertically, and it's got a cleavage in it as well. So these meta mudstone units tend to carry all the deformation. They're sitting above a huge thickness of competent solid rock that's very hard to buckle and fold, and you've got more of that at the Scala Conglomerate, as we'll talk about in a minute, above it. So this sort of squidgy layer in the middle gets all the deformation gets focused into it, and it just squidges and moves all over the place. So it's quite deformed, and it gave a lot of problems to the slate quarriers, because they'd find nice seams that were quite nice and easy to sort of create roofing slates, and other bits that were just a nightmare. This is the end of the bay here. There's a nice little beach here in the summer. A lady from here comes out and puts tea with a sort of a free tea with a donation, a thermos flask and cakes on a stand here. It's a beautiful place to come. Tea on the beach, and you can just wander down here. So I've wandered round the peninsula, across the little bridge here, and I've come on the other side of the bay. And then there's more slate quarries in the woods here, and on the foreshore they've obviously been hacking away at slates. You can see some slate debris here. So this is all part of the Jura Slate. As you go around the bay, you suddenly find there's a hard ridge of rock coming up, and that's telling you there's obviously a different lithology coming up. And you can see the dip. So we're going down the dip. We're heading southeast, and we're getting younger and younger and younger rocks. So here we've come through the Jura quartzite into the Jura Slate, and then there's a unit lying above us here that's harder. When you get to see it, you've got these thick, much thicker beds. You get some thin beds of mudstone, and these thick beds, basically of gravel. If you look at them in detail, here's one this is a detail one. You can see it's actually almost entirely made of sort of pebbles, small pebbles. There's an enlargement of it with my lens cap on it, so you can see these are quartzite pebbles mainly. So the Scala Conglomerate, this is what we're in now, is a very thick deposit of pebbly mudstones in a sort of beds, separated by beds of mudstone. And then the belief is that most of these are a sort of turbidite succession of stuff that was once in shallow water, and then maybe some faults have moved, there's been an earthquake, or something has happened to shift the sediment from the shallow water in a chaotic, destructive way to deposit these gravels in deeper water. And when there's no gravels being deposited, mudstone deposition was happening. So you get a background rain of mud interrupted by thick, gravelly turbidites. Which typifies the Scala Conglomerate in this area. So we're going to go north to Quarry, and this is the end of the road. Some wag has adulterated the road sign here, which is quite clever. But this is the end of the road. You've got a 4-mile walk to Barn Hill, and I say a 7-mile walk to Quarry and 7 miles back, and it's quite rough. You can't drive it. So you walk to Barn Hill. So we're going to zoom 4 miles to Barn Hill, and this is the end of the road into Barn Hill. It comes swooping down the hill here, and there's the wee farmhouse. Pretty much has Orwell left it. You can rent it as a writer's retreat, but it's fairly basic. But there's the view towards the mainland. So this is looking sort of north along the axis of Jura out to the top end. So though I'm not interested in the writing of the book today, although it's a lovely, good book, I'm going to talk a bit about the rocks that we see down on the foreshore down here. Here's a little map, another little map. So that photograph was taken from up here, and it goes down here. You can see the Jura quartzite again in yellow, and there's a whole chunk of Scala Conglomerate down here, and the junction between the two is pretty much next to the farm at that change of slope. So there's the farm, and you can take a little tour down here. I got a little walk I've put in the new book, which will take you down here, around the coast and round the coast, and then up here through some woods and back, a nice little circuit, and then you've still got your 4-mile walk to go back home again. Let's have a look at some rocks. So get down here, and what we find is, again, these are the turbidite sands. You've got mudstone here with a bit of deformation in it. There's some mud. Then there's a turbidite sand here with some mud in it, and you can see a few what I would think are probably slump folds. You can see these sort of things in here. Yeah. So and this top surface of this mud is sort of folded as well. So you get this is probably where this was unstable, and there may have been some sort of slope, and the thing would have been deposited, and then it would have actually sort of crept down the slope a bit. And as you go further around the coast here, some of these slumps turn into great big debris flows, and you get great big masses of chaotic boulders. And in fact, if you go onto Lung and Scaba, you find huge blocks sitting in the Scala Conglomerate. And I haven't got a picture of that, but I'm assured that that's the case. And you get some very, very thick gravelly sands as well. Here's one here, it sort of finds up a bit, and then it's got another little, topped by another little gravel bed on the top of that, yeah. And you get some more slump folds here. Here's this bed here, it's gone whoop, 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 done this, where other ones are straight. So, and then there's a mudstone unit, and then more thick, chaotic sort of debris flows and things. So a succession of unstably deposited turbidites at Barn Hill. And this is the sort of model that we used. I've used this as sort of model. Roger and I drew this thing out, or Roger drew it and I sort of amended it a bit. But basically we think that the Jura quartzite was deposited in a sort of a deepening sort of half graben. These are half grabens where this fault is moving, and it's creating what we call accommodation space. And the rocks are being deposited in this hole, and they're probably keeping pace with the down warping of this thing. As the crust extends this way, we're getting these faults, and we're getting holes formed. They're filling full of sediment, but they're probably keeping pace with the subsidence and keeping the sediments a sort of constant sort of deposition until we get to Scala Conglomerate times, when suddenly the faults are moving more actively, and we suddenly get a deepening of the basin and a more accommodation space and instability. So we perhaps get erosion up here on the footwall of the fault, and reworking of the scarber of the Jura quartzite and other rocks into these scarber conglomerates, which appear as sort of triangular shaped sort of and round sort of shaped fan deposits on the downthrown side of these fault scarps. And what's interesting when you look at the stratigraphy here is that the Jura Slate is actually time equivalent to the scarber conglomerate. So at the same time, we're getting a mud basin formed with these scarber conglomerate fans being deposited into it. And that sort of model. If you look at the north-south section, you get this. This is Barn Hill, and further north, there's less of the scarber conglomerate and much more of the slate. Up towards Easdale, obviously, it's virtually all slate. So, and to the south, it's just mainly scarber conglomerate on top of the Jura quartzite, and it's capped by the Port Ellen phyllites, which we'll look at in a minute, which is another meta-mudstone unit, but shallower water. This is deep water. Yeah, so this is shallow water, deep water, and then shallow water again. So a change in this unstable sort of slope that we can start to see at Barn Hill with these things being mobilized and then trundling off into the deep water, sliding off and creating erosion at the top of the Jura quartzite. Well, before I leave this section, I wanted to just put my oil geologist hat back on, because this is a beautiful example of what you would, if you saw this today in the North Sea, you would go for that as an oil geologist, because you've got reservoir rocks. The Easdale slate is quite organic rich still, so it must have been really organic rich in the late Precambrian, and you've got mudstones above. So the three things you need for oil fields are a reservoir, a source, and a seal. And you've got all three things here. And John Parnell, about a few years ago, did some thin section work on the scarber conglomerate and found graphite in what was the pore space. And his interpretation was that this actually is fossil oil. And so the sort of scarber conglomerate Jura Slate is a play in the parlance of oil geologists. That is, if I was a Cambrian geologist about 500 million years ago, I could have made my fortune here. Not today, because the oil price has collapsed. But anyway, you see what I mean. It's sort of, it would have been a good place to focus on. You're on a passive margin, and this sort of thing is going on in a rift setting, just like the North Sea. In fact, the Bray field in the North Sea is like the scarber conglomerate. It's actually very similar. So there's lots of analogies today. And the Bray field is a Jurassic fan into the Kimmeridgian shale, so which is the source rock. It's capped by Cretaceous mudstone. So exactly the same thing, but just a bit in North Sea, obviously a little bit younger and not metamorphosed. So the problem is here, it's been metamorphosed, and the oil has turned to graphite, to carbon, but it was oil once. Okay, let's we'll just head up to Corryvreckan, bit of interest. Here's a picture of Corryvreckan nicked off the interweb. I've been there in a rib, and you get, and it isn't one single, if any of you have not been there, it isn't one single whirlpool. The whirlpools keep forming at various times of the tide. And the boat, the guy with the ribs just sort of look for these sort of plug hole things, and then you put the ribs into them and they go round and round like a washing machine, and then he looks for another one and puts you a rib into another hole, and you go round and round like a washing machine. And that's all good fun. But anyway, interesting to see what the geology is of this whirlpool. Because this was the original interpretation. There was some sort of pinnacle, and the water was flowing over this pinnacle at tides and was forming this sort of a standing wave as it went over this pinnacle. That was the traditional interpretation until a few years ago. And then some high-res bathymetry was done, and lo and behold, no pinnacle. So the main thing is in here, and there is no real pinnacle in this area here. It's just there's obviously some sort of fault running through here. This is turned on its side a bit, by the way. But there's a fault running through here, obviously, and there must have been a glacial scour through this fault here that's causing the break between the two islands. So what is causing the whirlpool? And this is a sort of sideways view of that, but 3D view of that bathymetry. And the belief is that if you look here, there's a spur here, yeah, sticking out like a sort of like it's just one of the sisters of Glencoe or something like that. There's a sort of spur of rock there, and they believe that the swirling round as a tide hits this thing is actually, so it's a face of a scarp rather than a pinnacle that's actually causing the whirlpool to happen. So modern bathymetry is sort of solving the problem as to what was causing this feature. Quickly down, we'll leave the north coast and we'll head down to the narrow bit. This is Loch Tarbert here, and this is Tarbert settlement here. Very quick look at Tarbert. This is Tarbert Lodge, the home of Lord Astor, or they owned by Lord Astor, we believe, David Cameron's stepfather-in-law. And this is the house where last time I went there, it was a lot of security guys around because they were in it. And but this is where David and Samantha retreat to in Islay, in Jura. There's a lovely standing stone which has been adopted by a later Christian use, because it's got a great big cross carved into it. Yes, but so the cross is probably medieval, but the standing stone is obviously a lot older, Neolithic possibly. But this is a lovely standing stone at Tarbert that's quite well known. It's right next to the road. It's easy to get to. There's the road just behind that wall. So there's Tarbert. There's the standing stone here, and there's a lovely graveyard you can visit in here as well. So nice little interesting walk, nice easy walk down here onto the beach, round here and around here, and you've got some more. You're getting used to the geography, the geology now on these little maps. Jura quartzite, Jura slate, Scala Conglomerate, same succession. The thing is, you can see here that the Jura slate's quite thick here because these Scala Conglomerate fans are probably quite discrete and quite relatively small. So you get a thick fan section, and then you go along strike a few kilometers. This is 10 kilometers south of Ardlassa, and there's virtually no Scala Conglomerate, but quite a thick slate. And they've quarried it a lot here. Tarbert is the main slate quarry, or was the main slate quarry on Jura. And as you can see here, this has been hacked out by humans. And this whole foreshore is a whole mass of excavated slate quarries, like a mini Easdale, much smaller than Easdale, obviously, but in its day, it would have been quite a prolific workings. And here's the quarry. This is the floor of a quarry. They've been quarrying this here, and then this is the Scala Conglomerate. So they give up with this because once they got to here, they were into meta sandstones with the interbedded turbidites and things here, these thin turbidites, quite thicker ones as you go this way, but some quite thin turbidites to start with, and a slate over here. And there's a little boathouse here. Yeah, there's the boathouse. There's the ubiquitous deer, one of the 6,000 deer. They're very, very, for the ones, since the whole of Jura is designed around deer shooting, they're very, very tame. This one came within a few meters of us. Here's the Jura. There's a quarry here, usually, as often in the islands, full of junk. But this is the Jura Slate quarry in the sort of raised cliff here, full of farmyard junk. So we've been up here. We've been to Barnhill. We've been to Quarry Vrecken. We've been in Valassa. Just finished at Tarbert. I'm going to just nip down to here, look at some geology on the south coast here, and then I'm going to just finish up at the end, looking at the Paps and Loch Tarbert from the Ice Age perspective. But I'm going to look at some bedrock, a couple of examples of some bedrock down here, and then at the end of the talk, we're talking a bit about the Paps and Loch Tarbert and its Ice Age history. So this is Ard Finn, or Jura House, as it was once known as. This is what it was like when I went there about 10 years ago. Beautiful gardens. This is the old house as it was, but it's been taken over by Greg Coffey, who's an Australian hedge funder, and he's built an enormous golf course here. This is the house as it now all painted up white with the new extensions, and his swimming pool and orangerium and his farm over here, which is now the sort of estate headquarters. And this is all golf course. And the excursion that Roger Anderton put together in the 70s took you down here and all on the coast here, but it's not so easy to get to anymore because of this thing. I mean, I know access legislation allows us to do it, but you should still feel it trespassing. And if you look through a drone shot looking south, this is coming south along the coast. This is a beautiful example. This Jura quartzite, Scala Conglomerate in the cliffs here, the whole succession here, and then the Port Ellen phyllites and some igneous or meta igneous sills at the bottom here. So I'm just going to take you down to this bay here. So I wandered through the golf course here. All the turf and all the soil was imported from Yorkshire. Crazy thing, you know? And it's beautifully immaculate golf course, and it's just for him 2 weeks a year at the moment, as far as I know. Anyway, let's go down to the beach, down to the bay. Here's the bay, and here's the Port Ellen phyllites in here, and then this hard rock on this peninsula at the southern end here. And this is the Port Ellen phyllites. They're sort of stripy, sort of meta mudstone, meta siltstones, thin meta sandstones. Probably a shallow marine setting. I think we've come up away from the slate in the deep water basins of the Jura Slate and the Scala Conglomerate. We've got some much more sort of shallow marine meta mudstones, meta sandstones. Yeah, all dipping again southeast. This is looking into the cliff here, and this is all the what's called the Port Ellen phyllites. They're called phyllites, but they're not. It's just a meta mudstone, meta siltstone, meta sandstone sequence. Very little of it is actually a phyllite grade. Remember, phyllite is a metamorphic grade higher than a slate, which is supposed to have a wavy cleavage and a lot of mica in it. This never looks like that, so it's a bit of a misnomer. I'd like to call it the Port Ellen Formation. In fact, it's a good idea to take some of these lithological terms out of the lithostratigraphy and just call it after the name of the place. So this is the sill here. This is intruded into the Port Ellen phyllites as a dolerite sill, a horizontal intrusion into the sill, and they've been metamorphosed. And some of these sills have been intruded into those sediments when they were still wet near the sea and have reacted with the sea. So they've had two changes to the basalt. The basalt has changed because it's been reacting with seawater at the time of intrusion and has created some big phenocrysts of plagioclase, which have been altered by the seawater, and then it's been metamorphosed, and the feldspar has changed from a calcium feldspar to a sodium feldspar. A lot of the calcium has gone into epidote, and these are epidote veins. So it's a beautiful rock. In places you get this sort of sometimes finer and sometimes coarser grained stuff, and these big sort of epidote veins, which look like a great big stitch. It's like someone slashed it and then stitched it. You know, these look like this because there's a volume change when you get epidote. You get this sort of this contraction tension sort of thing here, and the sort of and these the very characteristic epidote veins in the sills. So green schist metamorphism of a basalt sill is basically what we're seeing here. But some of the sills had been what we call spilitized. They've been reacted with the seawater at 600 million years ago, and then green schist metamorphosed in the Ordovician at 470, and their chemistry changed yet again. So an interesting story to some of these igneous rocks. There are more igneous rocks if we just dip back up the coast to Barn Hill and Inverlassa, because we've got some Silurian age, 400 million year old rocks kicking around here. This is an andesite or a sort of microgranite at Lassa, and then we've got two intrusions at Barn Hill, a similar red andesite and what's called a lamprifier, a potassium-rich intermediate rock. And there's a lot of these intrusions along the coast, and they seem to follow fault lines that were probably developed at the same time as the Great Glen Fault at the end of the Caledonian orogeny about 440 million years ago. So there's a whole load of intrusions along the coast in Inverlassa and at Barn Hill that are slightly younger. Remember, the Ordovician was the time of the main deformation in the Ordovician at 470, and the Grampian orogeny part, the Grampian part of the Caledonian orogeny was then, and then the final part of the Caledonian orogeny was in the Silurian, with the Great Glen Fault and the Scandian event, and then you get these intrusions. So you do get some slightly younger volcanics, and these are post-metamorphic, so they're not metamorphosed, unlike the sill we saw at Ardfinn, which was a metamorphosed sill. It had been affected by the Caledonian orogeny. These haven't. They've been intruded into these deformed sediments. Okay, let's go down to the south coast. This is Ardfinn. We were there before. Going back down to the south, that's the Gulf. Now this is an aerial shot before the golf course got taken. That's all golf course now. But I want to tell you, there's a little island here. There's a little island off the coast. It's got a little tide running in here. So there's a little tidal island called Glacial, just up the coast, up towards the ferry. Let's just take you there for a wee visit. Here's a very badly put together panorama of it from the coming down off the road here. This is Isla in the background. This is the Sound of Isla here. And then we went there at a very, very low tide deliberately, so we didn't have to get too wet to get across to the island, because I wanted to go there, but I didn't fancy getting wet. So we went there when the tide was very low and we could just walk across. Not a problem, not a problem. I was a bit nervous when I got there. I didn't want to get trapped on it, so I didn't spend a huge amount of time on it. But it's got these reddish brown sort of crumbly lavas on it, yeah. And some amygdoidal lavas with the vesicles filled here and sort of other surfaces here. And these are Permian age lavas. And you think, what are they doing on Jura? But there is a whole bunch of lavas on this island. And they've been dated by Brian Upton at 284, I think, which is earliest Permian. So what are they doing there? This is a bit complicated, this slide, but this is a geological map of Isla and Jura, and I've stuck in the latest bathymetry from the same stuff that you were seeing up at Quarry, and I've just stuck in some bathymetry here. So this is shallow, the reddish, greens and yellows are getting deeper, blue is the deepest. So off Port Askaig, which is about here, the Sound of Isla is the deepest. And you can see here on this enlargement of that bit here. And there's our island, yeah, here. And there's another outcrop. These skerries out here, which have got a buoy on them for the navigation, are also the Permian lavas. And there probably is a sort of fault-controlled little half-graben. So it dips this way, it dips in this way. So there's a little half-graben of Permian rocks. And when you look at the more regional geological picture, you can see it's the tip end of a sort of this is green, is a sort of Mesozoic age basin. This is Triassic, Jurassic, and it may have even Carboniferous stuff in it as well. So Isla and Jura are, the purple is all the Dalradian. If you took the sea away, you would just see all the Dalradian of Jura and Isla going out over to Colonsay and all that stuff, and a big ridge here over to Northern Ireland. So that's the purple is the Dalradian stuff, and this green is this younger Mesozoic fault-bounded half-grabens. The Lochindale Basin to the south of the Rins has got 2 kilometers of Triassic rocks in it, and the Rattling Trough similar, a lot of Triassic, Jurassic rocks in it. And the little Permian lava field is right up there in the tip end of this thing. And it looks like there's a fault running down the Sound of Isla that separates Isla from Jura. There's always an explanation for these topographies. There's got to be a reason why there's a great big dirty hole right down between the two there. And there is a fault running through the system, through there here. I've been looking at this, quite interested. This is a map of, this is a geology map of Isla and Jura. And if you look at this dike, there's a Carboniferous dike that cuts across here. And it suddenly appears here, and it appears here. And sort of, if this is going to work, let's see. Yeah, there's just highlighted the green Carboniferous dike, and you can see it's offset, and there's some faults. So it looks like we've got not just a down-throwing fault, we've got a sinistral offset. You can see this thing probably goes to there under the sea, then it's faulted to there. So it's slid left as you look down on it, yeah? And this one has gone left as well. So we've got a whole sort of sinistral fault. And when you go along the coast, along the ferry here, from the ferry and walk, this Jura Quarry is shattered to hell. It's completely smashed up. You can't see any bedding. It's just a fault zone. So we've got quite an interesting fault zone here. In fact, the bounding fault down here that bounds the Jura quartzite is probably goes up to here and is offset and comes back up here. So some interesting geology that's not on the geological map, because the geological map doesn't show the seabed. Right, where are we going now? Oh, Ice Age. Yeah, how are we doing for time? Perfect. Let's talk about this is where Isla and Jura are at the time of the ice, and it's Glacial Maximum, 27,000 years ago. The black was the edge of the ice, which is right out the edge of the continental shelf, and Isla, Jura, well under ice, possibly even a kilometre and a half of ice at the last Glacial Maximum 27,000 years ago. And these are obviously, these are sort of time contours of what the ice may have looked like as it shrank back as the melting started to take place. So by 16,000 years ago, Isla and Jura would have been at the edge of the ice. By 15, they would have been clear of ice. So that's the sort of time we're looking at of when the ice was hovering around Isla and Jura. It was there quite thick 20 odd thousand years ago, and then it really started melting between 20 and 15. By about 14, it had pretty much gone. And here we have a sort of timeline of sort of temperature, sort of proxy temperature. So this is where we are now in the Holocene. Then we have this little, and this is the main glaciation in here. There's LGM is the last glacial maximum, 2020, there's 2019. Then we get the melting phase, and then a very strong heat. By 14, we've got very temperatures like today. But there was a sudden dip into this thing called the Younger Dryas, this sort of cooling event that happened about 12,000 years ago, probably when the North Atlantic circulation was cut off by a huge fresh meltwater from the North American continent and caused a sort of a cooling in the Northern Hemisphere. And that has big effects on Isla. So we've got cold, getting warmer, warm, sudden cooling, and then warming again. And see what happens. So this is Loch Tarbert. Remember we saw Tarbert here and down here. I did a canoe trip down here. Some of you have seen pictures of my canoe trip, sea kayak trip that we did out to the west coast of Jura to see some of these raised beaches down here. You can see this is actually the Jura quartzite. You can see here, and it's actually cut. You can see it's cut by all these faults here as well. So it's quite interesting. It's not just, you can see all these are slabby. These are all these southeast dipping chunks of rock, but they're cut by these quite strong fault lines. And there's one through here that causes this lock to occur, and then you get this sort of raised beach or composite raised beach here that sort of dammed up the lock. I'm going to just take an enlargement of this area here. This is the sort of the classic area of the raised beaches on the west coast, and it's divided into two main geomorphological features known as the high rock platform and the main rock platform. The main rock platform is pretty much at sea level, or close, just above sea level, and it's terminated by a backing cliff, which is quite a prominent thing. You can see it quite well in this aerial shot here. Yeah, and then you've got the high rock platform, which is terminated again by a backing cliff, but the back is a bit more obscure. But this is a backing cliff to the high rock platform. This is about 30 to 50 meters above sea level here. This is just about 10. And then the high rock platform is actually draped in shingle ridges. You can see all these beautiful shingle ridges here, and they're formed as the sea level would have risen to here and then gradually fell as land rose. So when this ice melted at 15,000-ish, 14,000, sea level quickly rose, and the land rose slowly after that and pushed the sea back. And these are regressive ridges. Yeah? We know they must be older than we think. This cliff line here was formed in the Younger Dryas times when there was a period of periglacial weathering and relatively constant sea level. And these shingle ridges are truncated by this and by this platform. And these are younger. These are post-glacial gravels. These are pre-glacial or late glacial gravels and shingle ridges on top of it. So we've got quite a lot of geology or geomorphology in this picture here, and there's some pollen work being done on these wee lochans in here to try and understand the sort of timing of the events of all these various ridges and when they formed and when they but there's basically a time. They go this way in time. They get younger and younger and younger this way. So maybe 15, 14, 13, 11, 12, and then bang, they got this erosion event here. Way to get to it is on a kayak. So there's the Thames of Jura. This is the kayak I borrowed, and there's one of the first sort of. This is the beach here that's blocked by the loch, and that's blocked by these big shingle beaches. And this is probably a late glacial barrier, and then a younger post-glacial beach down at the bottom here. And further on, when you from the kayak, you can see these late glacial gravels going up to 30 or 40 meters above sea level, with a post-glacial beach and a Holocene or recent beach lower down. So a lot of different beaches at different ages here. And then this is a shot of the height of the main rock platform, 5 or 6 meters above sea level, with these caves, abandoned caves here. So these were formed 11,000 years ago in the Younger Dryas. And there's the sort of composite view of the late glacial beaches here, truncated by the main rock platform, and then the main rock platform down below, and the recent beach here, and Colonsey in the background. And there's a picture of it all happening. There's the high rock platform. The high rock platform is probably pre-glacial and may have formed 3 million years ago in the Pliocene. was followed by ice in the Pleistocene, 25,000 years. The maximum big ice sheet would have, but it would melted. It would deposited a till or a basal till, which is still there in places. Sea level rose, and then it started to fall and formed a whole series of these late glacial beaches, the orange ones, which sometimes sit on till. You can see them in places. If you dug down, you see the till underneath it. Then you get the Loch Lomond re-advanced, the Younger Dryas times, and the formation of this main rock platform with sea stacks and caves, periglacial thing. There's the icebergs floating in the sea, but it wasn't glaciated. It was periglacial. It was tundra. It was a lot of sea freezing and thawing, a lot of freeze-thaw weathering, and a relatively constant sea level to form these this geomorphology. Then the sea level rose, reworked a lot of the debris, yeah, and then the sea level finally fell as the last bit of raise isostatic uplift happened. So we get that little raised beach, little perched beach, and a modern beach. So you get a modern beach, post-glacial beach, raised late glacial beaches. So quite a composite picture. It's not just a simple story. Let's have a look at some paps of Jura. This is Ben Chiant. This is Ben Ur, the highest of the paps. This is the middle pap. This is the northern pap, taken from Corabin, the baby pap. And so I'm looking south along strike here. You see the dip of the quartzite in here. Yeah. And the feature I'm looking at here is this. Yeah. This is this sort of lobate form of sort of scree on the east flank of Ben Chianti. And in the 70s, a paper was written on this saying this was the best example in Britain, perhaps the only example in Britain, of a rock glacier. And it was described as a rock glacier, then redefined somewhat later as a protalus lobe. So the terminology starts getting a bit complicated, and then it was redefined then as a discrete debris accumulation, as probably as a catastrophic rockfall. So sort of three different interpretations of this thing. Here's a close-up view of it, of this sort of arcuate sort of frontal ridge of it here. But there are issues. I mean, there's actually bedrock here, and there's some bedrock here, and there's bedrock in the middle. So it's not quite as simple. And there's that's a sort of maybe a slightly younger feature sitting on top of it. And is this one different? Is that just merged? Is that another one that's merged into this one? So is it not a simple feature anyway? Is it quite a composite feature? But nevertheless, if you had a textbook example of a rock glacier deposit, this is what you would expect to see, and that's how it was described. So here's a little cartoon I just knocked up to show the difference between these three things. So a rock glacier is basic. I mean, it varies depending on who you talk to, but I would define it as a sort of a rocky glacier. Basically, the glacial surface is full of rocks. It could have been all sort of rockfall on top of it, but it's basically cored by ice, and ice is the main transport mechanism. So if you dug down in here, you get ice, and then when it melts, you obviously get a rock deposit, but it's actually a sort of slow movement downhill of a glacier covered in rock. A protalus lobe seems to be more of a mixture of rock with interstitial ice, and it sort of creeps. Yeah, it's sort of permafrost and creepy down, but it's not solid ice. It's just sort of a mixture of ice, slushy ice and rocks and a sort of mess, and it just sort of creeps down the hill. But when it melts, the ice melts and again leaves a rock deposit, which doesn't look very dissimilar to this. And the one on the right is just pure rockfall with no ice at all, and that can produce the lobe as well. So the three different and they all grade into each other. And if you did a graph here of ice increasing this way and debris this way, so you've got talus and rockfall, which we've got no ice but lots of debris at this end, and a nice white pristine glacier in the Antarctic at this end, which has got lots of ice but no debris, and everything in between. And so I've just drawn this very simple. Another glaciologist would probably draw it slightly differently and have different terminology, but this seems to make sense to me anyway, that this is increasing amounts of ice in a sort of in an environment where there's a lot of rockfall going on, a lot of rock incorporated into it. But the latest interpretation is that it's probably is more like this than it is like this, for various reasons. And this is the latest interpretation from Dave Jarman, is that basically at the top of the hill, there were lots of slippages of rock, which then accumulated in a pile up here. So there was sort of several stages of slipping and accumulation of stuff. And then there was some catastrophic event that just catapulted the lot off into here. And it hit the ground running. And that's what, and the sort of bounce back and the sort of wave at the front of the avalanche caused the ridge to form, the sort of frontal lobe ridge. So it wasn't just a slide of creepy rocks that you would get maybe in a sort of scree. When you walk on a scree, you get the rocks start trundling. This was probably a major catastrophic event that just wham, went straight down here, bounced and hit the floor, because it was already accumulated a huge big pile at the top. Just from the top of Bien Chiant, you can look at Ben Hur, the highest point of the Corbett. That's the highest point of the Paps. And I just wanted to show you a picture of this piece here from a different angle, from the summit ridge. Actually, looking at this bit here, there's a sort of this is looking northwest. Yeah, and there's the summit of the hill here, and the belief is that this rock ridge here has actually used to be there. This cliff used to be there, and the whole thing has slid down the dip to there, lubricated by melting water. It was, so something has gone on to detach this piece of rock from its sort of resting place up here. Yeah, this is a slide plane. And also the other Pap has a big catastrophic rockfall thing as well here. This is a lot more chaotic. It's not as low bait as that, but obviously, and you can see it probably come out of this bit. So this may be just a single event from here where all this stuff just came from here and whoosh down here, and then you form this sort of big lobe here. So what's going on? So imagine that you've got, before the glaciers, you've got a nice little valley with a nice little stream, and here's your southeast dipping strata. Then you put a glacier in here, over deepen it, the rocks are still dipping like this. And when the ice melts, these slabs up here are just unstable, yeah? And they're just, this is where you can get, so they've been buttressed by the glacier, eroded, and then the glacier ice has held them in place, and then take the glacier away and they become unstable, and that's when they can start crashing down. So this is a phenomenon known as de-buttressing. Before I leave the Paps, I wanted to just show this picture of the Paps from the other side. This is from the Isla side, and there's a feature here. You can see this line down here. This is known as the old witch's slide, or the old lady's slide, Scrobda Caelic, and it's a sort of big train of boulders that come down and down and down and down off here. Just zoom in a bit. So this is Ben Hur. This is where that Camelback, as it's called, that split ridge up there with it was up there, and they get this big line of boulders here. And this is actually, if you look at the literature, this is perhaps one of the only examples in Britain of a medial moraine. Medial moraine, because there was a glacier coming this way and a glacier coming round the mountain the other way, and this was probably at a time when this was a nunatak, or a bit of sticky out rock, and the ice was wrapping around Ben Hur, and there must have been some catastrophic rockfall up here that dumped rock onto this glacier, but the two streams both picked up a bit of the rockfall and then merged it into a sort of a medial moraine. But it is one of the few, perhaps the only good example in Britain of a medial moraine. Just a bit of science for you. Some of this stuff has been dated, and what you can do with cosmic rays. Well, cosmic rays cause breaking of the oxygen in quartz to beryllium, and the silica goes to chlorine. And you can, very high-tech lab in East Kilbride, you can actually measure minute quantities of beryllium-10 derived from oxygen-16 by cosmogenic rays. And what happens is that if you've got a boulder in a moraine, and then it's in the ice, it's not seeing any cosmic rays because it is better in the ice, and then suddenly you take the ice away, it gets cosmic irradiation. And from the ratios of the oxygen, the beryllium to the oxygen and the chlorine, you can actually date when the ice went away. You can date, so it's exposure dating. It's telling you how long that rock has been sitting in the sunshine since the glacier melted, and it can give you some very interesting results. So I go to a map of the Paps. This is Corabin. This is Ben Shanty with its so-called rock glacier sitting here. This is Ben Hur with its little notched ridge thing here. There's your Scrobda Caelic going up that way. There's the moraine, and this is the one here, the Ben Caelic with the rock slide that I showed you earlier. And the little red boxes are the exposure ages, and you can see here they're 15, 14, 13. The original interpretation of this as a rock glacier was that it was Younger Dryas, and it would, therefore, if it was Younger Dryas and a permafrost or an ice-cored rock glacier, it should have had an exposure age of 11. but it doesn't. It's 15, and it's not. It's a time when everything was melting. So that the whole debuttressing rockfall comes as a much more plausible explanation for this than it would be now that we've got this dating. In 1970, Alistair Dawson didn't have access to this wonderful new technology. So it just shows you that the science changes and changes the interpretation. And we believe that the paps are formed from the breaching of these coals by an enhanced over-breaching of these coals by flow of ice. So this is the main flow of ice during the main part of the glaciation, which should have gone this way, and probably at the very end of it at 16, this was a nunatak sticking out, and the ice went round here and deposited and the rockfall was up here, and it deposited the medial moraine here. But as the ice melted back further, it became a long strike, and it became much more northeast southwest, and it did this direction, which is slightly later. And it's this debuttressing, this event here, that caused this debuttressing of the effect on the southern flanks of these hills, and all these unstable southeast facing slopes all collapsed, possibly as uplift was happening, earthquakes were happening, as uplift was going on. So maybe they were triggered by an earthquake. So they were unstable rock masses, and then suddenly they catastrophically collapsed due to some sort of earthquake due to the isostatic uplift. So another little story. So this is a sort of what Jura would have looked like at the Glacial Maximus. This is an ice divide or ice shed. You've heard of watersheds. This is an ice shed. This is ice stuck to the ground, and it's flowing out across Jura and Isla out to the edge of the continental shelf in the last Glacial Maximum. If you could sort of imagine what life would have been like 15,000 years ago, 16,000 years ago, you'd have had little nunataks of ice sticking out of the paps, the ice here, and the flow much more in a sort of northeast southwest direction. Yeah, so you've got these two ice flows, one that way in the maximum, and then as it waned this way. And in fact, all the striations you see you see rock striations on Jura both directions. We know that the ice was covering. You used to think that the ice never really got over the tops of these things, and I'm going to go back. I'm just going to nip back 2 slides. So these things called block fields. These are block fields on the tops of these mountains here, yeah. And the thought was that these were never covered by the ice, even at the glacial maximum. These were always nunataks, and these block fields were freeze-thaw weathering on the tops. A lot of work's been done on that recently with the beryllium data across Scotland, and these block fields are now thought to be all relict, and they are where the ice was stuck to the mountains, and so that we believe that these hills were completely overrun with ice, because if you read the literature up to about 7 or 8 years ago, it would have said that the ice thickness on Jura was about 700 meters, and these poked out the top. It's probably more like it was twice that thickness, and these were well covered at the glacial maximum. And it wasn't until we get to 17,000 years that we actually get the nunataks right at the very end of the glaciation, and as it then switched to this flow to this flow. So there we are. Thanks for listening. I think that's how we're done. That's perfect timing. Time for a dram. I always finish my walks with a recommendation for whiskey. This is my favorite Jura malt, but on Jura, sorry, you have a chance for gin as well from the Lusser Gin ladies. They're lovely gin. I'm talking again this week. Email me if you haven't got a link. And I'm going to talk about Snowball Earth and Isla on Thursday at 6:30. So thank you.
Thank you.
Oh, fantastic.
Very good.
Thank you.
Thank you.
I don't know where we are.
Thanks very much, David. It's absolutely brilliant. You started off with a geology map with only 3 rock types, and I thought, oh, this is going to be nice and simple. But it was anything but. A really very brilliant mix of stories there. Thanks very much for giving us a tour. Feel free to stay around the chat if you want, folks. If you have to get away, that's great. Anyone's got any questions, ask away, or you can type on the chat if you prefer. I'm sure David would be very happy to chat further.
He said she'd be ready for 7:00.
Can I just ask you about the relict scree on the block fields at the top of the... David, so you're talking about these being from previous interglacial, then they basically sat around embedded in ice on the hilltops.
it rose up when they've looked at some of the Torridonian mountains, and they've got Torridonian sandstone block fields with lumps of Cambrian quartzite in them, and think, how did they get there? And then when they started doing the exposure dating on it, the whole story started to unravel that these things weren't nunataks, these things were covered. And the reason for the block fields is that the ice was frozen solid. It was just cold ice frozen to the substrate, and it flowed around the mountains, but the mountains were actually the dead spots.
Yeah.
So that seems to be the explanation of why we get the block fields.
I done a few trips around Edinburgh and up to Cairngorms with Michaela Newton, who's originally from Romania. And in the early days when she was first doing trips, she was fair. English is really, really good, but she used to talk about the ice flew over here and it flew over there, and sadly someone eventually corrected her. But it was just such a nice kind of vision of the ice flew here and the ice flew there. That's what I was really thinking. What really amazes me when we're looking at the paps is just how much scree there is. Yeah. And it's really nice. It's so complicated, all the different parts of that story in terms of when the screes form, but presumably a lot of it is post-glacial shattering of exposed quartzite, because the ice must have stripped off a lot of previous screes and taken it away.
Yes, absolutely. I mean, this is all fairly recent scree stuff. I mean, the Younger Dryas would have been a time of severe periglacial erosion, and it hasn't been removed by anything since then. So, you've got a lot of freeze thaw weathering, water into cracks. It was a very severe time, that period when the North Atlantic almost froze over. It may have been North Atlantic may have been ice covered.
Yeah, it's amazing. There's some questions coming through on the chat. Dave's asking about cosmogenic dating. Would the boulder not have had cosmic rays before glaciation as well?
Well, yeah, I guess that depends on where the boulder was. Naturally, they take lots and lots of samples and they eliminate the outliers. If they find a weird one that's obviously had a lot of exposure, but it's about getting a pattern. So if you get 20 samples all with the same age and then a few that are completely different, then you know what you're dealing with.
Yeah.
You just can't take one sample. It's the same with any science. One sample doesn't make a summer.
Yeah.
So so you will get some boulders with a strange history and some other stuff. And I'm not an expert on it. And Dave Jarman and Colin Ballantyne are the sort of the guys that know this stuff well. Someone asked about the glaciation in the Medial Moraine. Would it not have been destroyed? No, possibly. It obviously wasn't. I mean, I think the main ice flow would have been would have focused on the Sound of Jura to the southeast of Jura was the main glacial trough. Yeah. So I mean, good point. I hadn't thought of it, but yeah, I mean, obviously, it's that north flank of the didn't get wiped clean at all. It's a lovely place to go. When you think of the glacial history of Jura is fascinating. If you're into geomorphology, it's a brilliant place to go. And some good geology, bedrock geology. It's not just 3 rock types.
Worth going just for Medial Moraine in its own right. Just considering how most of us probably first heard about medial moraines when we were at school. It's one of these weird things like Oxbow Lakes that you kind of pick up. But I'd never thought of it before.
I think it's the only one. It's pretty much the only one we know of. So it's a long way to get to it as well.
Brilliant.
Sorry, it's an extremely stupid question, but I mean, I'm just trying to understand, how the paps of Jura stayed, didn't collapse completely, because I thought often, the rocks that were harder, igneous and whatever, stayed, and the others were, so to say, taken away by the glacier. But I mean, so why is this kind of, why are those 3 paps, so to say, so much higher? I mean, why didn't the glacier take them off as well?
Well, I think it nearly did. I think if it had gone on a bit more, we'd have lost them all. They were being very eroded.
So they were, so to say, on the edge.
Yeah, when you remember I showed you there was sort of northeast, sort of northwest, southeast fault lines, and I think the glaciers picked those up. So the whole thing was crisscrossed by faults, which turned it into like a chessboard of blocks,
Uh-huh.
and so the ice goes between goes that way and that way, and cuts it up into sort of big squares. And what we're left with is 3 or 4 big squares left in the middle. So the rest of it's much more eroded. And
Mm-hmm.
so someone, you could use the word Inselberg, yeah?
Yeah, so they are, so to say, like an intermediate state between much higher mountain and then what after a longer time would have been practically flattened.
Yes, it's just that the ice didn't completely get rid of them, but yeah,
Yes.
it did a pretty good job. But it's a lot of rock there to move. There's 5 or 6 kilometers of rock to shift.
Yep.
That's a lot of rock to move.
Yeah. Okay.
So this golf course is just for his own private use, is it?
Yeah, well, there was talk about this year he was going to open it up a bit, but obviously that's been stuffed a bit. But apparently he goes there 2 weeks a year. A whole entourage comes a month beforehand. All his clothes, photographs, pictures. The whole place is done up for him for 2 weeks holiday. So what can you do when you've got a hedge fund of gazillions of money? It's 4 houses, I believe, like this. It just rotates around them. It's another world.
Absolutely.
The thing is, the population are split because some of them, like the old place where you can go to the Jura House gardens, you put £1 in an honesty box and go around the gardens. Now you can't go there, and yet many people on the island work for him.
Yeah.
So, he does provide employment for greenkeepers and gardeners and housekeepers, and I mean, there's a whole team of greenkeepers that spend all year trimming and mowing, or maybe 1 or 2 rounds of golf.
So amazing echoes of Kinloch Castle and Rum from the Bullock family. Did exactly the same. They arrived for the season and left again, and there was staff there all the time, just keeping things running.
History has a habit of repeating itself, doesn't it? But they are the modern day Bullocks.
Yeah. Kind of get more respect for. Maybe not. I was just thinking
It's
that
still a
money
lovely
is
island to
derived
go
from.
visit. I mean, and you can get to it on Isla. You can get to it in Isla for a day. So you stay on Isla, you just dip over on the ferry and you go up to Barn Hill and do the walk to Barn Hill, and then get all the way back, pint in the Jura Hotel, and get the ferry and go home. Lovely.
Fantastic. Any other questions from folk?
Someone said there's a story he brought a plane load of Italians in late March, bringing the virus with him. I've not heard that story, but I'd love to follow it up. As far as I'm aware, there's no virus on Isla and Jura, but this could have been kept very quiet. So it's a good story anyway. I'll look it up, and I know the local paper has never reported that. But yeah, interesting.
Well, thank you very much, David. We'll let you get away and prepare for your next talk on Thursday. Thank you so much for spending the time.
I got to do
Great
2 in a
story.
week, but anyway, yeah. If anyone hasn't had a link to and wants to come to Isla on Thursday night, then email me, please. I'll send you the link and password. But yeah, we're going to do a sort of it's a virtual field trip. So we're going to do a trip where you actually walk virtually along tracks and bogs and moors, and we see rocks in the way you would see it in the field, rather than just a sort of cook's tour that we've done this evening, where we jump all over the place. This will be rocks as you would see them if you were on your hind legs with a hammer in your hand.
Fantastic. And
Okay.
we'll come back to Collinsay maybe next week.
Yeah, I could do Collinsay. Yeah, I can do a relatively short one on Collinsay. It's a smaller island and only 2 rock types on it, he said.
Brilliant. Thanks very much.
Thanks.
See you soon.